I saw a video go around on social media that was talking down on anyone that doesn't create their own models. To me, it brought to light that there may be a lack of variety on sites like Printables. So why not put some options out there? If you watched my tensile testing video, you would know that I don't have a vise. I could buy one off Amazon or Harbor Freight for like 30 bucks, but why not design one that can be 3D printed? I want to create a vise with a 3D printed primary structure that can achieve at least a 500-pound clamping force. I chose 500 pounds because I have clamps that are rated to 300 pounds, and they weren't quite enough when pressing in coupling nuts into the braces on the tensile tester in a previous video. I would like to be able to bolt the vise to a surface just like a standard vise, but I would also like it to be able to be clamped to a desktop. I don't normally index a vise when using it, other than 90 degrees, but I would like for anyone who uses it to have that option. So the vise will have to interface with a desktop or surface, as well as my fixture plate or any surface with bolt holes. The jaws of the vise will also have to be able to clamp onto a variety of materials and shapes. Let's take a look at a couple options already available. The most reasonable option would be to buy an inexpensive vise clamp off of Amazon. It has all the features that one would expect from a standard vise clamp, and it's only $30. However, I can't 3D print it on my printer, and it only has a 3-inch jaw opening. Now, Concept 2 really has my attention as it is fully 3D printable. It is cool and it gets a lot of things right. However, all of the threaded components are 3D printed. While I think this is cool and I do like it, the plastic would significantly reduce the amount of clamping force that the vise can handle without failing. Also, the rotation locking method wouldn't be able to handle much torque transfer through the vise without the screw failing. The screw also appears to be the only thing that is holding the base body to the base top body, which limits the amount of upward force that can be applied to the vise jaws. Finally, there isn't a way to bolt the vise to a surface. Concept 2 is pretty cool, and the Amazon option is the most financially responsible option if their only desire is to have a functioning vise. But I think I could make something cool that will check all of the boxes. I may be in the airport while writing this, but it won't stop me from starting the design. I don't feel like I want to get too creative with the design on this. I feel like a more standard look may actually stand out on the 3D printing websites. I know that I want to be able to rate this at 500 pounds of clamping force, and I learned from the bending attachment on the tensile stressor that the thickness will likely have to be at least 1.5 inches thick. I have leftover 5/16 hardware that I can use, as well as some random metric stuff. I want the jaws of the vise to be replaceable like in a standard vise, but I think it may be a good idea for the jaw screws to be on the side of the vise. This would allow a reduced chance of a fastener making contact with a part being held in the jaws. Also, it can be relatively easy to pull out the heat set threads inserts in comparison to shearing them out. I really want to focus on the strengths of 3D printing, so the different pieces will be dictated by avoiding relying on layer adhesion rather than the strength of PETG. Because I want the vise clamp to handle a good amount of torsion, the indexing feature needs to be able to withstand reacting shear forces. I think a spur gear or torque similar pattern should do a great job of this. I can print this in parallel to the print bed, and the vertical portion of the vise clamp can be bolted to the rotary plate. The rotary plate could then be bolted to the base with as many fasteners as the user wants. The base should have the imprint of the rotary plate so that they can interface. I will mimic the same pattern around the base diameter to allow for plenty of bolting options for the base to a surface. I will have to make the clamping base in 2 separate pieces due to the 2 different loading scenarios. And this is the result. After throwing it together in CAD, I did decide on some small changes on the fly and was forced to make some other changes. The change I didn't have a choice of is the rotary base pattern. I initially wanted far more teeth to allow for smaller angle adjustments, but my FlashForge Adventurer M5 couldn't handle all of the curvature at the firmware level. After days of troubleshooting, I decided to print the part on my Creality Ender 3 V2, even though it would take over 3 days to print. Then, of course, the Ender decided to start layer shifting. I fixed that, noticed the print quality was degrading even though I just changed the nozzle, and then the hot end stopped hot ending towards the end of the print. I ended up writing off the Ender 3 V2 as not worth putting more time and money into, and bought the Ender 3 V3 KE on an Amazon flash sale. I then had to go through the process of multiple prints to tune in the settings for the Overture PETG that I normally use, but then just ended up buying Creality PETG with their provided settings, and finally got the part printed. The stock settings with the Ender 3 V3 KE are very ambitious, but it prints without issue. The part surface finish was just a bit wavy, which is really just a cosmetic thing. I had gotten some pretty good quality PETG prints with the Overture filament, but I honestly just got impatient with tuning the flow ratio to stop layer stepping. I got close, but it was at half the print speed of the stock settings at 150 millimeters a second, and 0.92 flow ratio being the top level settings. It looks like I will have to drop the flow ratio further. Anyways, back to the design. So I had to settle with far fewer teeth. I found a very inexpensive handle nut and McMaster car that would be held in place with 2 flange nuts, and a thrust bearing in between those and the front jaw, allowing for rotation. A handle could be printed, but I like a solid handle that won't flex a lot. There are a couple more nuts on the other side of the front jaw to allow for retraction. Finally, the threaded rod screws into a coupling nut that is pressed into the rear jaw. I decided to use standard threaded hardware because they were less expensive than lead screw hardware, and the standard threaded hardware should work fine. I included a feature for removable jaw pads that take M5 screws on the sides. This allows for customization with different materials and textures. I intended on printing mine out of TPU to create an even softer jaw than PETG. In the end, I decided to not have a secondary plate for bolting to a surface because the rotary plate itself could be used for that purpose. Actually, you could even bolt the rear jaw directly to a surface using the fastening points at the bottom. That makes 9 3D printed parts, 15 M8 screws, 9 M8 threaded inserts, 7 M8 T-nuts, 2 M5 screws, 2 M5 heatset threaded inserts, and various other hardware pieces. It looks like the highest amount of bending stress in the front jaw would be at the plane that goes through the center of the primary screw. Now, to be honest, I printed the parts before doing the analysis, which really isn't the best idea. So I'm just going to find out what I may rate the vise based on the 10mm shell that I printed the parts with. I did also print at 80% infill, but again, there's no industry standard way to include that in the calculations by hand. If we were to look at a section view at the lead screw attachment point, we would actually end up with 2 hollow tubes with 10mm walls that are sharing the clamping load. I treat one of these tubes as a beam with one fixed end and the load applied to the other end, then it just becomes a simple bending problem. After finding my known values, I can algebra the bending stress equation into the max rated force for the beam with a maximum allowable stress, that is the material yield stress, divided by 2.2. I can then multiply that force by 2 for 2 beams and get a rating of 681 pounds with a factor of safety of 2.2. Now that I have a load rating, I can move on to the coupling nut since it will probably dictate how thick the walls will need to be when I print this part. Because we were applying a load in this direction, the coupling nut must have an equal and opposite reaction. This looks like we're going to try to pull the coupling nut out through the PETG with 681 pounds of force. The stress is easy to solve for using the perimeter of the coupling nut and the thickness of material that the nut would be pulled through. Speaking of that, It is important to note that the material is going to have to be solid around the perimeter of the coupling nut. Therefore, I'm going to have to print with walls of about 10 millimeters thick. At this point, we only get 258.1 psi of stress, giving a factor of safety of 13. The last area I was concerned about was the stress in the rods. For some reason, I just had a hard time wrapping my brain around how to properly solve for bending stress in the rods. Now, instead of reviewing how I may calculate this by hand, I found an open source FEA software called Prepo Max. I ended up spending a couple days trying to figure out this software. It definitely isn't ready for prime time, and I ended up having some super simplified model that gave me a maximum stress of just about 2900 psi in the threaded rod, which is nothing compared to the yield stress of the 4140 steel at 100,000 psi. So it should be more than good to go. As a bonus, I have learned a new tool to help my next project, which would be incredibly annoying and complex to solve by hand. I'm excited for that one. Now that I know that the vise won't implode, let's get this thing put together. I started by heat setting the T-nuts into the base plate. I did end up using my heat gun in the end to speed up the process. I then went to install the threaded inserts that were meant for softwood into my plastic. I decided to heat up the plastic beforehand in order to prevent layer splitting. The rear jaw ended up warping while printing, so while installing the threaded inserts, the layers ended up splitting apart, even though I preheated the plastic. It wasn't that big of a problem though. I ended up just filling in the cracks with plastic with the same welding methods that I've done before. Then I pressed in the threaded inserts for the jaws. After heat setting the T-nut into the desk clamp, I finished assembling it. I then installed the coupling nut using a wooden dowel and a hammer, making sure that an edge is upward on the coupling nut in order to match the imprint that I have within the rear jaw. Before starting the final assembly, I need to add about 2 inches of threading to the guide rods on one end. I use a chamfer tool in order to help me start the die. When installing the first flange nuts, I decided to thread the flange nut onto the rod and then forced it beyond the threads in order to lock the threading into the aluminum rod. Unfortunately, I don't have a way to properly test the clamping force that is being put out by this vise. I can tell you that it had no issue clamping onto my other clamp, which I'm sure is super useful to know. I also found out that the solid PLA benchies are surprisingly strong, as I couldn't crush it. If I were to remake this video, I would use a thicker rod so that I don't get as much deflection. Probably a 1/2 inch or 13mm diameter threaded rod. Then the front jaw would definitely be the weak point. However, that would also mean a lot more money spent on hardware. In the world of Chinese manufacturers selling products at material costs, it makes no financial sense to make this vise. However, it definitely can have a lot more character than the others. Here's how much it cost me. The hardest hitter is the filament. The final weight of the assembly is 11.4 pounds. I'm gonna guess that's about 2 pounds of it is hardware, so the rest would be about 9.4 pounds of PETG or 4.3 kilograms. So if you had no filament to start, you would have to buy 5 1 kilogram rolls of PETG. I set the price to $20 for a kilogram of PETG, but if you keep an eye out for sales and aren't picky about color, a kilogram of PETG can be had for as low as $14. The hardware pricing is approximately based on McMaster-Carr, and most of the numbers are rounded. I use 316 stainless steel bolts, but you can get steel bolts for as low as 30% less if you don't mind the chance of some rust. I wasn't super precise on this, but my total came up to $134.46, and I will round that up to $140 in case I missed something and for the silicone tape. $140 actually isn't terrible of a cost to make when Chinese manufacturers aren't selling steel vises at or below production cost. I also like the unique look I got from using partial spools through the prints. Of course, we're not including labor here, but I definitely learned something and had fun doing it. If you want to create this vise for yourself, or maybe even just work off my CAD model, I left a link to printables in the description below. Thank you for watching. Please consider liking, commenting, and subscribing. Don't forget to share this video with anyone who might be interested, and thanks for sticking around.